Hello and welcome back to this series on linear algebra. So in the last video we covered spanning, and I asked you the following question. Do the two vectors I2 and was it I2? No, sorry, 1i and I2, do they span the complex numbers of dimension 2 over C? Okay, so essentially, can any complex number be written as a linear combination of these two vectors here? And so I hope you had a go at that. And so today I'm going to be going through the answer, and we're going to be finding out if they actually do span complex numbers. So recall, what does span mean again? So let's go back to the definition of span. Span means if I've got a vector x, then that vector x can be written as a linear combination ax1 plus an xn for all x1 up to xn and a1 up to an, where x1 up to xn are in our field and a1 up to an are in these are in our vector space, so in our set, and these are in our field. So that's what spanning means. So we're going to look at this. So how can I go about solving this kind of question? So if I take a generic complex, a generic vector in this field, which would be, say, the vector, so wx, so we could have w and u. Can this be written as a linear combination of these two vectors? Oops. So there we go, plus a2 multiplied by I2, where A1 and A2 are complex numbers. How can we go about solving this kind of question? Well, one way we could go about solving this kind of question is by using Gaussian elimination, which I'm assuming you've already covered before. So how does Gaussian elimination work? Well, let me just compare these coefficients. So if I have WU here, this is equal to, we've got A1 here, we've got A1 times I, plus I've got A2 times I, and I've got 2 here times A2, so 2A2 here. Well, I can write these in terms of a matrix, okay? And I can solve a set of simultaneous equations. So comparing the coefficients, we have that W on the top must be equal to A1 plus A2 times I, and then U must be equal to A1 times I plus 2 times A2. So here's a system of two equations here. And if you notice here, I can write these in matrix form, which I've already said. So this would be, so this is having, down here, the equivalent of having 1 here, I here. We've got I here and 2 here. And this is called an augmented matrix, okay? So I'm assuming you've seen this before. And we know that a solution exists if we can solve this augmented matrix. Okay, so let's go ahead and see what we can do via Gaussian elimination. Well, so we want 0 instead of an I here. So we want row 2 to go to row 2 minus I times row 1. And then we have the first row will stay the same. We get 0 here, and then we have 2 minus Well, we have I times row 1. Well, I times I squared is minus 1. So that's 2 minus minus 1. So that's 2 plus 1, which is 3. Okay, so I'm going to go put 3 here. And on the right hand side, we'll still have W, but then we have U minus I times W. Okay. Oops, my mistake. So that is... Let me just go here. So let's just check that we've done everything right. So what do we have? Yep, that all checks out. And now we've got it in this form. Well, this is called echelon form. So it's spelled like this. Echelon form. And when a matrix is in an echelon form, you can find the rank of the matrix. And the rank is, just to remind you what the rank is, the rank is the number of non-zero rows in any echelon form. Okay? And when you know a matrix has the same rank as its number of rows, so here's 2 rows and it's rank 2, given the matrix is, well, given the matrix doesn't have a contradictory solution, so this would mean that the solution contradicts, so it would be saying something like 5 equals 4 or something, then it is solvable, and it has a unique solution. So this equation does indeed have a unique solution, and you can go ahead and, well, you can either solve it or you can put it in reduced row echelon form, and then you can find the exact solution. Now we have the following propositions, which says, let V be a vector space over a field F, and let x1 up to x1 be in V. Then the span of x1 up to xn is the smallest subspace that contains the vectors x1 up to xn. And furthermore, if x is in the span of x1 up to xn, then the span of x1 up to xn and x is equal to the span of x1 up to xn. And secondly, for any a2 up to an in F, we have that the span of x1 up to xn is equal to the span of x1, the span of x1, x2 minus a2 x1, up to xn minus an x1. Let me just edit this. ANX1. Okay, and here's some notes about this. So I'm just going to explain, I'm going to unravel what this actually means. Okay, so what this is saying is that firstly, the span of the vectors, which I've listed, is a subspace. Okay, that is important, that it's a subspace and it contains those vectors. And among all of the subspaces with this property in V, it is the smallest subspace. So basically, if W is a subspace of V and it contains these vectors, then the span of these vectors listed, it lays inside of W, okay? So you can't find another subspace with this property which doesn't lay inside W. And secondly, B implies that the span of the column vectors of any matrix do not change when performing row operations. So essentially this lets us perform row operations, and those row operations will not change the span, okay? We've seen this with the previous example, but it's important that we prove this for any matrix, okay? So we can do this under any Gaussian elimination. Okay, so here goes the proof. And it goes like this. So firstly, we need to show that the span of x1 up to xn is a subspace of V. And how do we show this? Well, we go through our axioms. So the first axiom is the zero vector contained in this? Well, the zero vector can be written as the zero element of the field times x1 plus all of these elements of multiples of the zero vector, of the zero element of the field, times x1 all the way up to xn, okay? Right, really I should be putting vector notation, but you should be familiar that these are all elements of a vector space anyway, and so they are all vectors. And this is indeed contained in the span, by definition, okay? By definition of the span, alright? So that's contained in the span. And secondly, if we let x and y be in the span of x1 up to xn, well, this implies that there exists an a1 up to an, which is in the field, and there exists a b1 up to bn, which is in the field, such that x is equal to a1 x1 plus an xn, and y is equal to b1 x1 plus bn xn, right? And this is by definition, okay, of the span. Then we have the following, so x plus y is equal to a1 x1 plus b1 y1 plus an xn plus bn yn. But now we can use commutativity and associativity, and we get that this is equal to a1 x1 plus b1 x. Oh yes, sorry, my fault. This is, we have already used associativity here and commutativity, okay? This was implicit. We've used associativity and commutativity of vector spaces here to go from this step to this step when we've added them, okay? And then we can use the distributivity axiom, and we can use that to pull out certain elements. So we have, this is equal to a1 plus b1 multiplied by x1 plus an plus bn multiplied by xn, and this is using distributivity law. Okay, this is using the distributivity law of a vector space. And now we've done that, it's pretty simple. We've got a1 and b1. We've already said they're in a field, so a1 plus b1 is still an element in the field. So this is in F, and this is also in F here. And these are vectors in F, sorry, these are vectors in our vector space, and this is just the definition of span, okay? So, hence, these are contained in the span. Up to xn. And now we've got a third property to prove. And once we've proven this, we've proved that the span is a subspace. Well, this is pretty straightforward. What we do is we say that let x be in the span, okay, of x1 up to xn, and a be in a field F. Then we can just write x as the linear combination of a1 x1 plus an xn with a1 up to an in F. And we know what x1 and x1 are by definition of the span. And then we can use the first distributivity law to multiply both sides by a. And then we can pull the factor of a out. So if we multiply every term by a and then we pull the factor of a out, then this is a times a1 x1 plus ANXN. Okay, so we've multiplied the left by A, and so we've got to multiply the right by A. So we multiply everything by A, and then we pull A out. And we find it is indeed in the span.